relation between the Cp and Cv. So what is Cp? Cp is actually molar heat capacity. So we already studied that molar heat capacity at constant pressure is Q by N into delta T. If you take N equal to 1, then it becomes your molar heat capacity at constant pressure. So like this Cpm, that delta Q upon Qt. So Q can be heat evolved or heat absorbed. Similarly, Cv is equal to delta U plus N delta T. So N is the mass of the gas, delta T is change in temperature. And if you take N equal to 1, so this becomes your molar heat capacity at constant volume, Cv. Cvm means molar heat capacity. This is the heat capacity. Both are different. Now we also study that empirical relation, this H is equal to U plus RT. So if you take this for N mole, if you take per mole then of an ideal gas, then this becomes your HM is equal to UM plus RT. So HM minus UM internal energy at molar, internal energy, molar internal external enthalpy is equal to RT. So when T is, this temperature T is increased by delta T, then molar enthalpy increases by delta M, then molar internal energy increased by delta UM. So we can write this delta HM minus delta UM equal to R into delta T. Now if you divide by delta T, so this becomes your molar so change in molar enthalpy by delta T minus change in molar internal energy, internal energy by delta T, and this delta T will cancel equal to R. And this is nothing but the, already we know that this CPM or CVP. So you can see here, so the one derivation relationship comes, that is Cpm minus Cvm equal to R in terms of molar. And again this is greater than Cpm. Why? Because at constant pressure all the energy, constant volume, at constant volume all the energy supplied as heat to the system remain inside and temperature rise accordingly. So when temperature rise, all the energy is supplied as heat is inside the system. In this case all the heat is inside the system. But in constant pressure what happens, some of the supplied heat escapes back into surrounding. This is the only difference. In these cases at constant volume all the heat is inside the system, but in these cases some of the heat is escape back into the surroundings. Then the system expands. Now that what happens, it only happens when system expands and some work is done. So definitely less energy remains in the system and temperature does not rise as much, so which corresponds to the greater heat capacity. So we can also write Cp minus Cv. So work done by the 1 mole of gas in expansion when heated through 1 degree centigrade. So work done by the gas at constant pressure is P delta V, and for 1 mole of the gas at PV equal to RT, so N is equal to 1. So when temperature raised by 1 degree centigrade, then volume becomes V plus delta V. So we can write this one, equation 1, PV RT. So PV means V is become V plus delta V. So we can write P into V plus delta V, and R is equal to R into T plus 1, because this is raised by 1 degree centigrade. So 1 degree centigrade. So we can write PV delta R, because PV and RT this will be equal to each other. This will be cancelled. So we left P delta V R. So we can write Cp minus Cv equal to P delta V or R. And Cp minus Cv is also called as the Mayer's relation. And one more you have to remember the formula of thermodynamics, Cp by Cv is equal to gamma for the ideal gas, and Cp by Cv is nothing but the Poisson's constant, or it is called as heat capacity ratio or isoentropic factor. Its name is isoentropic factor. So gamma used for actually determine the atomicity of the gas of a gas. So atomicity is number of atoms. So gas may be monatomic, diatomic or polyatomic. So monatomic is helium, neon, oxygen, nitrogen, helium, so hydrogen, or polyatomic means diatomic or polyatomic, carbon dioxide, ammonia, sulfur, trioxide, methane. For this one Cv is at 3 by 2R, and for monatomic, diatomic is 5 by 2R, polyatomic is 3R, and Cp is Cv plus Cr. So add it by R to get the Cp. So 3 by 2R plus R, 5 by 2 plus R, and 3R plus R. So if you take the ratio, you will get the 1.66 monatomic, 1.40, 1. So this is decreasing order. And again, the gamma depends upon the atomic of the gas molecules due to the degree of freedom for molecules. I hope that you have studied degree of freedom in thermodynamics. So different movement of the molecules in 3-dimensional. So for monatomic molecules, energy is actually translation energy, but if you take the diatomic molecules and polyatomic molecules, So there are three type of energy they possess molecule. One is translational, and for translational, vibrational, and rotational. So it is I have written wrong. So this will be your uh, vibrational, and this will be your rotational. So these are the energy will be possessed by the diatomic and polyatomic molecules. And you have to also note it down. The specific heat of the steam is this much calorie per Kelvin per gram, and the specific heat of ice is 0.5 calorie per Kelvin per gram. And if you take the specific heat of water, that you know that 1 calorie per Kelvin per gram, that is 4.18 joule. The larger is molecule, greater is its heat capacity. Second point, and the water has the large heat capacity due to strong intermolecular force of attraction. Now let us take some Na and Nb is the moles of two non-reacting ideal gases. There are two ideal gases, one is A and B, and their moles are Na and Nb, and these gases are mixed, they can mix. So we can find out the average heat capacity at the constant volume of this mixture, these two gases non-reacting mixture. So we can write moles into Cva plus moles into Nb into Cvb and divide by number of moles of Na and B. If you take 3 moles, then you can write Na, Nb, and Nc, Na, N plus B like this. This is the one formula. So suppose there are helium whose Cv is 3 by 2R, oxygen whose Cv is 5 by 2R. So their Cv for different gases is again different. So when these 2 moles of helium is mixed with the 4 moles of oxygen, find the Cv of the mixture. So nothing. Cv of the mixture is 2 into 3 by 2R plus 4 into 5 by 2R divided by 2 plus 4, and then on solving you will get 13.6R. Now let us see some numericals. A sample of ideal gas whose gamma is 1.4 is heated at a constant pressure. So if an amount 140 joule of heat is applied to the gas, and find the delta U and work done by the gas. So delta H is nothing but the QP, NCP in delta T, and internal energy is QB into NCP delta T. So we can convert that is NCV. So if you divide this Cv by Cp into Cp, so we can write this N Cp T2 minus T1, and this is Cv by Ct. So we can, this is nothing but this is called as the Qp, and it's Q by Cp. So Q by Cp is 1 by gamma. So substitute the value, you will get answer 100 joule. Then what is work done by the gas? So work done by the gas will be your delta H is equal to delta H plus P delta V. So P delta V is work done. So P is equal to P delta V, and substitute this value, you will get 140 minus 100, that is 40 joule. 5 dm cube of an unknown gas at STP requires 52.25 joule of heat to reach its temperature by 10 degrees centigrade at constant volume. Calculate the Cp minus Cv and atomicity of the gas. So Qv is equal to NCV delta T at constant volume. So substitute this value, so you will get Cv equal to this much. And this, what is N? N is nothing but the, you can say, moles of the gas, that is the volume of the molecule divided by the volume of the molecule at STP. So we will get this much moles. So this is that 0.25 is this much moles. Now Cp is equal to Cv plus R, this much value, and gamma is equal to Cp by Cv, that is 1.4 will indicates that this is an diatomic gas. The enthalpy change delta H for the reaction is, this is the reaction, and it is enthalpy change, this is given minus 92.38, and you have to find the delta U at this temperature. So this is the formula. Delta H is equal to delta U plus moles of the gas into RT. So we can write delta U is equal to, this is the value, this is the delta NgRT. Delta Ng means, you can see 2 minus 4, this is 2 molecules, product of the gas molecules minus product of the sum of the moles of the reactant. So 2 minus 3 plus 1, 4, this is 3, this is plus 1, 4. So you will get here minus 2. So on solving this into minus 10 to the power minus 3 into 298, so you will get this much kilojoule. Since this is in kilojoules, so we have to convert into here in 10 to the power minus 3, because this is in joule, R is joule. So to convert into kilojoule, we have to take 10 to the power minus 3 into this. Then this is equal, so we will get this answer. So keep careful in putting the unit. If this is kilojoule, then you put in 10 to the power minus 3. If it is joule, then you remove this one. This is the way of solving question. Enthalpy of combustion of cyclohexane C6H12 is this much at 25 degrees centigrade. Calculate the heat of combustion at constant volume. So this is our equation and delta H is given. So use this formula. So again delta H is given, delta U have to find out. Delta Ng is 6 minus 10. This is 6. This is a liquid. Liquid is 0. And gas is 9 plus 1 10. So 10 minus 6 4. So it is minus 4. And this into R into T. So you will get this answer. The heat of combustion of naphthalene, the C10H8 is this is solid at constant volume was found to be 5 minus 5133 kJ per mole. Calculate the value of enthalpy change at 298 Kelvin. This much answer you type by yourself. The internal energy change for the reaction, this is the reaction, is 8 minus 8 is 5 kJ per mole at this much Kelvin. What is the enthalpy change of the reaction at the same temperature? So again use this formula. Delta H is equal to delta U plus delta Ng RT. So delta Ng is you can see here 1 minus 3, so minus 2. Now substitute the value. Delta is this much, R is this much, T is this much. So again this is kilojoule. So again you multiply 8.31.2 then per minus 3. You will get this much answer. Now to guess A2 and B2, they are giving A2 and B5. Delta H at 27 degrees centigrade is found to be this much joule. Calculate the internal energy change for the reaction same temperature. Again use the same formula. Delta is given, delta U you have to find out. Delta Ng will be again 2 minus 7. So this becomes this much Ng, R and T. You will get this much answer. Since this is a joule, so you have to write only this much. If it is kilojoule, then multiply this into 10 power minus 3. So keep in mind while using the R. Calculate the difference of heat of reaction at constant pressure and that at constant volume for the combustion of 2 moles of liquid benzene at this much temperature. So this is the reaction. So if you delta Ng will be definitely 12 minus 16, 12 minus 15 because these two are liquid. Cancel 12 minus 15 minus 3. Use this formula, substitute the value, you will get answers minus 7.43 kilojoule. Calculate the value of delta U of the following reactions. So this you try yourself. This is the reaction and delta H if you get is this much. So you can find out delta U by yourself. The reaction cyanamide with dioxygen was carried out in a bomb calorimeter and delta U is given this much at 298 Kelvin. So calculate the enthalpy change for the reaction at 298 Kelvin. So use the same formula as above. You will get answer this much. This is our answer. For a gas having molar mass m, specific heat at constant pressure can be given as. So there are 4 options. So what is the specific heat of this process? With options. So thermal capacity specific heat capacity is given by Cp minus Cv for n moles of gases R. But if you take the in terms of specific heat capacity, this is really Sp minus Sb minus R by m. So this becomes a per mole. So what is Sp? Sp is the heat capacity at constant volume. Sb is the heat capacity at constant volume. This already we have studied. And Sp by Sb also written as the gamma. Similarly, Cp by Cv is gamma. Specific heat capacity at constant pressure and specific heat capacity by V for the ideal gas is also written in form of gamma. Now you substitute the value of this one. Sb, that is Sp by gamma. So Sp by Sp minus Sp, and instead of Sb you put here Sp by gamma. By using this relationships you will get this is equal to R by 1. So Sb is equal to Sp by gamma. So putting the value you will get Sp equal to R into gamma divided by m into gamma minus 1. So if you see this one, so answer A is correct. Like this is our answer which is correct. While studying the property of the gases form C2, Cl2, F2, is the chlorofluorocarbon, a chemist cooled 1.25 gram of a sample at 1 bar pressure from 323 Kelvin to 293 Kelvin, and during cooling the volume of sample decreased from 274 ml to 248 ml, and calculate the delta H, delta U of the process. Cp is given this much joule per mole per Kelvin. So we have to find this one delta U. So first what is delta H? Delta H is NCP delta T. We have 2 formula, one this formula, 2 formula. Delta H can be found out by this formula. So Cp is given, N is given. So what is moles? Moles is 1.25 by 133. So molar mass of chlorofluorocarbon is this much. So you will get this moles. So NCP into delta T. So N is given, Cp given, delta T is given. 293 minus 323 Kelvin. So this much is the delta H. So now by using this formula, delta H is equal to delta U plus P delta V. So delta U is, that is the delta H, pressure is 1 bar and volume is 26 ml is given here. 26 ml means 274 minus 248 ml. You can see here. So on subtracting you will get 26 ml. Now convert into liter. So if you convert liter, this becomes your 26 into 10 power minus 3, and 1 bar liter is equal to 100 joule. 1 bar liter is equal to 100 joule, so multiply by 100. So use this formula carefully, because if you miss these type of things, you cannot get the result. So only these type of things are very carefully. If you are using 1 atmospheric liter, formula will be different. For 1 atmospheric liter, formula is different. So again you subtract it. On subtracting you will get this answer. So this is the answer of this question.